So the next unit in this topic is looking at periodic trends. So we've looked at the periodic table. Now we're going to look at some trends in the periodic table. So these are your learning objectives that you should be able to know and be able to do by the end of this particular subunit. So the first thing we'll look at is the atomic radii. Okay, so it's basically how big the atoms are. And as you go across a period, you will notice that they get smaller and smaller. Reason, of course, being that you've got more protons, there's more positive charge, it's pulling on those electrons, so it's making them closer to the nucleus. And as you go down the group, you're obviously going to see an increase in atomic radii as the number of electron shells increases. In terms of cations and anions, when you take an electron away to make a cation, then the cation's obviously going to get smaller because you're going to have less negative charge, more positive charge. So more positive charge means more pull on those electrons that remain. And with anions, they're going to get larger because if you add an electron, then there's more negative charge. So there's less of that positive charge to be shared amongst the extra electron. Okay, so that's what you're going to see. Cations are going to get smaller as you go across, and anions are going to get bigger. And as you go down, the cations are going to increase, and the anions are also going to increase. So we've already looked at this in the last topic. First, ionization energy. So it's basically the energy required to remove one of those electrons from the atom to make it an ion in the gaseous phase. We've already discussed that in the last unit, so if you need further assistance, then go back and have a look at those videos and PowerPoints. But basically, as a summary, the ionization energy, or IE, increases across the period because the nuclear charge increases. So there's more effective positive charge attracting the electrons as the number of electrons in the shell is increasing. And as it goes down the group, because electrons are now further away, and so there's less effective positive charge, because also you've got the shells, electrons and shells closer to the nucleus, shielding those outer electron shells. You've got two anomalies. Okay, so boron has a slightly lower ionization energy than beryllium because the 2p electrons are slightly higher in energy than 2s, so it takes less energy to remove those electrons. And anomaly number 2 is oxygen has a lower ionization energy than nitrogen because the p orbital only has one electron, and the extra electron ends up in oxygen, causing a pair of repulsion, okay, to make it easier to remove, hence giving a lower ionization energy than nitrogen. Okay, so another important concept in chemistry and the periodic table is the electron affinity. So it's kind of the opposite of ionization. It's basically the energy release when 1 mole of electrons is attached to 1 mole of neutral atoms, okay, in the gas phase. So you're actually adding now to form anions, and obviously it's going to increase the affinity as you go across because you've got a larger positive charge because there's more protons, so there's more affinity for the electrons. And it's also going to go up as you go up the group because you're getting you're getting closer and closer to the nucleus, so there's more attraction of the positive nucleus to that extra electron which you are adding. And that's also based on electronegativity. I'm also going to provide a short video which will assist hopefully with it, but it's essentially electronegativity is the concept, is an ability of an atom to attract a bonded electron pair to itself when in a covalent bond. Okay, so fluorine over here, it's a very small, tight atom. Okay, the electrons are tightly bound to this, or attracted to the nucleus because there's lots of protons. So it's easy for fluorine to grab an electron, okay, from a neighboring atom in a covalent bond because it's a small positive charge basically of the nucleus. Whereas something like sodium, being a metal, it wants to get rid of its electron, not get one. So it wants to give away its electron, so it has lower affinity. So it's only got an electronegativity of 0.9. Okay. So you can also see the general trends as well. As you go down the group, you've got less electronegativity, which makes sense in a sense because you've got further distance away from the nucleus. And as you go across, you've also got the increase of electronegativity because, again, you've got increased positive charge as you go across. So more ability for the electron to be attracted to the nucleus of the corresponding bonding atom.
I really can't express how wonderful and useful the periodic table is, especially this pretty one that lists the electronegativities of most of the elements. Electronegativity is the ability of an atom of an element to attract electrons when the atom is in a compound. The higher number means that they have a higher affinity for electrons, and the electrons will spend more time near that element. You don't have to memorize all of these if you notice that there's a general trend of increasing electronegativity toward fluorine. But maybe you noticed that the noble gases don't have electronegativity values. That's because only a few of them will even react with other elements, and it's under some very specific circumstances, so their electronegativities are unknown. When two elements with very similar electronegativities bond, like hydrogen and carbon, they form nonpolar covalent bonds. Electrons are shared fairly equally. When elements like hydrogen and fluorine bond, they form polar covalent bonds, where they are shared unequally. When elements like francium and fluorine bond, their electronegativities are so extreme that sharing doesn't even happen. It's bullying, and fluorine straight up steals the electrons. But you know how in kindergarten a boy might pick on a girl because he has a crush? Well, after the stealing occurs, the atoms become attracted to one another and form an ionic bond. Or an ironic bond. Okay, no, just ionic. Thanks for watching this episode of Teacher's Pet. Don't forget to like and subscribe and follow me on Twitter at SciencePet.
Okay, so in terms of metallic, non-metallic category, you may have already worked it out that metals have small electronegativity values, non-metals have high values. So if you calculate the difference between the two electronegativity values that are given, differences of greater than 1.8 will usually form ionic bonds rather than covalent bonds. So in the previous example, fluorine with 4 and sodium with 0.9, 4 minus 0.9 is 3.1, a very strongly ionic bond. So these are basically the summary of the trends. Okay, so as you go down, the atomic radius increases. As you go across, the electron affinity and ionization increases. As you go up a group, the ionization energy increases, the electron affinity increases. And as you go across, back the other way, across the period, atomic radius is going to decrease. And as you go, I guess, towards the group 7, group 8, you've got more non-metallic character. Going the other way, it's more metallic. So that kind of summarizes all the different properties and trends in the periodic table. Okay, so I'm just going to look at a few examples of different groups and their properties. Okay, so alkali metals, they have low melting points and boiling points. And the reason for this is due to increased shielding and less neutral attraction between the associated metals. They're very reactive because they want to lose that one electron from their valence shell, and they are large atoms, so they're soft and very dense. Okay, not quite metallic in that sense, because they don't tend to have a luster because an oxide layer quickly forms on their surface. And you should know from IGCSE that they react very easily with water to form, even explosively, to form sodium hydroxide, at least for sodium, so a base plus hydrogen gas, and the hydrogen gas is the reason why you have the explosions, due to the heat generated. And alkali metals and halogens also react very readily together, vigorously to form the associated salts. In terms of the halogens, they are also very reactive for the opposite reason. They want to take in electrons. They're very electronegative, so they just want to gain that one electron. And their melting and boiling points are due to increased London dispersion forces, or IMFs, so that's intramolecular forces. Okay, they're between the simple covalent molecules of the halogens and the increased molecular weight as you go down the group.
The halogens are the elements in group 7 of the periodic table. They are fluorine, chlorine, bromine, iodine, and astatine. In this lesson, we will learn about the halogens and their key reactions, the displacement reactions, reaction with metals, and reaction with hydrogen. Halogens in their elemental form are toxic, though their compounds have many real-life applications. The halogens all have 7 electrons in their valence shell and can accept 1 electron to form an ion with a -1 charge. Moving down the group, atomic radii increases by 1 electron shell. As a consequence, melting points and boiling points and their density also increase. To illustrate this, fluorine and chlorine are gases, bromine is a liquid, and iodine and astatine are solids. Fluorine is a very pale green gas. Chlorine is a greenish-yellow gas. Bromine is a reddish-brown liquid. Iodine is a gray solid that sublimes to a purple vapor. Astatine is a black solid and radioactive. Moving down the group, the reactivity of the halogens decreases. So a selected halogen is always more reactive than the halogens below it. A more reactive halogen will always displace a less reactive halogen in a compound. We will demonstrate these displacement reactions using aqueous solutions of potassium chloride, potassium bromide, and potassium iodide. Note that these are all halogen-containing compounds. When we add chlorine water to an aqueous solution of potassium chloride, no reaction happens. Since chlorine is more reactive than bromine, chlorine will displace bromine in potassium bromide, producing potassium chloride and liberating bromine. The resulting solution is reddish-brown due to the presence of bromine. A similar observation occurs when chlorine water is added to an aqueous solution of potassium iodide. Since chlorine is more reactive than iodine, a displacement reaction will occur to liberate iodine according to the reaction below. A dark brown solution is produced due to the presence of iodine. Let's predict what happens when bromine water is added to the same 3 aqueous solutions. Please pause the lesson to think about this and resume once you are done. When we add bromine water to aqueous potassium chloride, this causes the solution to turn reddish-brown, but no displacement reaction occurs as bromine is less reactive than chlorine. No reaction occurs when bromine water is added to aqueous potassium bromide. As bromine is more reactive than iodine, it will displace and liberate iodine in potassium iodide. Therefore, a dark brown solution is produced due to the presence of iodine. If we added iodine to the same 3 aqueous solutions, no displacement reactions occur, as iodine is less reactive than both chlorine and bromine. Halogens can react with certain metals to form metal halides. A very common metal halide is sodium chloride or regular table salt. Sodium chloride is extracted from the sea or from salt mines. Sodium chloride can be produced from the reaction of heated sodium metal with chlorine gas. Since it is a highly exothermic reaction, it is not recommended that this be done in a laboratory. Halogens can react with hydrogen gas to produce the corresponding hydrogen halide. Most of these reactions are also highly exothermic. As an example, chlorine gas and hydrogen gas can react to form hydrogen chloride. In summary, the halogens are the group 7 elements.
Their displacement reactions involve a more reactive halogen displacing a less reactive halogen in a compound. Halogens can also react with metals to produce the corresponding metal halides and can react with hydrogen to produce hydrogen halides.
Okay, so looking at the halogens, what they look like. So halogens become darker as you move from gas to solid down the group. So if they're arranged, so you start off with fluorine gas, which is a very pale yellow. Then you move to chlorine gas, which is getting a darker green. Then you move to bromine, which is again a liquid now, which emits a brown vapor. And then you have iodine, a solid that sublimes into a nice, pretty purple gas. Okay, and halogens higher up the group will displace those of the lower down, as you can witness here. Okay, we'll do an experiment on it as well, because they are essentially more reactive. Okay, so fluorine is more reactive than chlorine, chlorine's more reactive than bromine, bromine's more reactive than iodine. Okay, so just to summarize that, the more reactive halogens, which are further up the group, will take an electron from the halide ion. Okay, so this electron, it gets taken by the more reactive chlorine, and that means that it forms the associated chloride, and because the electron's now been taken, the bromine will form molecular bromine, the bromide will form molecular bromine. Okay, so that's what happens when halogens react with the associated halide ions. Just to finish off, looking at the oxide reactions and related link to pH. So the oxide of the elements have increased acidity across the period. So as you go across the period, you get to a point where aluminium, for example, is amphoteric, which means it has both acidic and basic qualities. Metal oxides, therefore, tend to be basic. Non-metal oxides are acidic. Okay, so you get increasing acidity across a period. So sodium forms very basic sodium hydroxide in solution. Manganese oxide, very basic manganese hydroxide. Phosphorus forms phosphoric acid, getting acidic, and sulfur dioxide and sulfur trioxide both react with water or dissolve in water to form the associated sulfurous acid and sulfuric acid. These equations, of course, have to be learnt. And that's pretty much it for periodic trends when it comes to IB chemistry.